Good evening. My name is Jesse McDowell, and today I will be discussing the derivation of mass transport equations. First, let's go over the mass transfer of diffusion. As you can see here in this diagram, the particles at the top are plentiful at t equals 0. You probably can't see it that good on here, but as you decrease to like t equals t1 and t equals t2, it gets less and less. So by the time it's t equals t3, it's only a few particles at the bottom. Now when you get to this box at t infinity, in the z direction, and it's just also in the z direction, it's empty. That's because it's at equilibrium. And this pretty much explains the mass transfer from high to low concentrations, as my study group members also indicated in their videos. It also shows the net transfer equals 0 when the concentration is uniform, and the heat transfer rate is proportional to the area or the cross-sectional. This first equation here is for momentum flux, and it's saying that momentum flux is equals to Newton's law of viscosity, which you would recognize in your unit operations or transport. Also, it has the heat flux formula, which is equal to the negative thermal conductivity times the temperature gradient, which is the heat conduction. Next, it goes on to explain that the molar flux of the binary mix of A and B is the molar flux minus the diffusibility of A and B times the change in concentration of A divided by the concentration gradient divided by the change in distance. And that's Fick's law of diffusion. Also, we have here the total concentration, which is represented by J, A of X is equals to the negative concentration of DAB times the change of moles of A divided by the change of distance, which is the mole fraction, and the diffusion of coefficient. The molar flux, the mass flux, is represented by a lowercase j, which is equals to the negative density times DAB times the change in WA over the change in distance, which is the mole fraction, mass fraction. Here we have the molar average velocity, which is represented by Vm, which is equals to summation R times Ri times Ci, which is the component I times the concentration of I over the total concentration. And that equals the total net molar flux over concentration, which is equal to the flux of A plus the flux of B divided by the concentration. Over here we have that the velocity of A times the concentration of X is equal to length divided by time times mole divided by length cubed, which equals the units for flux, which is moles over L squared times time. And here we have the velocity, the molar average velocity is equal to the velocity of A times the concentration of A plus the velocity of B times the concentration of B, which is equal to the moles of A times the velocity of A plus the moles of B times the velocity of B. And VI represents the individual species of velocity, which is equal to NI, which is the flux of I over the concentration of I, times the and that equals the mole fraction of I, which is equal to the concentration of the individual species divided by the total concentration. Here we have VID, which is represented by the diffusion velocity of that same species is equal to the velocity of the independent species minus the velocity the molar average velocity, which is equal to Ji over Ci, which is the flux of I over the concentration of I. Now this part is for the stationary coordinate system, which says that an individual species, which is Vi, is equal to the flux of I over the concentration I, and that the moles of I is equal to the concentration of I over concentration. And this is derived from that, which is saying that the flux of I divided by the concentration of I is equal to Ji over Ci, which is the flux of I over the concentration of I, plus the flux of A plus flux of B over C. And the same thing is reiterated down here, which is the flux of I is equal to the flux of I plus the divisibility of I plus the concentration of I times the flux of A plus the flux of B. And here we have the flux of A is equal to the diffusion flux of AB times the negative concentration times the change in moles of A over the change of distance plus the moles of A times the total flux. And it's the same for the moles of the flux of B. And there you have it. That explains the derivation of mass transport equations, and that concludes our group's presentation for this project. Have a good night.